Hello there. In this video we're going to introduce an integral identity that is used on integrals that perhaps has a horizontal or a inverse type of shift associated to it. In particular, the identity that we're going to be looking at, and also a generalized version, is the following. Namely, the integral from 0 to a of f of a minus x dx is equal to the integral from 0 to a, so the same exact integral bounds, of just the basic function f of x dx. So we're going to prove this result and also do a couple examples and also develop its general form as well. Alright, so the first thing we're going to do is prove that this identity is actually true. So, proof. So we're going to consider this identity, the integral from 0 to a of f of a minus x dx. And we're going to assume that a is some positive real number. So we're going to use a u substitution, so we're going to let u be equal to a minus x. So that means du is going to be negative 1 times dx, which means that dx is going to be equal to negative 1 times du. Let's also look at our integral bounds as well. So when x is equal to 0, we have that u is equal to a minus 0, which means that u is going to be equal to a. And when x is equal to a, this implies that u is equal to a minus a, which implies that u is going to be equal to 0. So our integral from 0 to a is going to go to a to 0. So that means star is going to be equal to the integral from 0 or a to 0 of f of u times negative 1 times du. So we know that if we have a negative 1, we can actually flip our bounds here. So this implies that our integral of interest is actually equal to the integral from 0 to a of f of u du. And since this is a definite integral, this u is actually a dummy variable, and we can actually write this as the integral from 0 to a of f of x dx. Therefore, we have proven that the integral from 0 to a of f of a minus x dx is precisely equal to the integral from 0 to a of f of x dx. So very easy proof. So let's illustrate this with a very basic example. So example. Let's assume we want the integral from 0 to 4 of, let's do the cube root of 4 minus x. Yes, you can probably use u substitution on this, but we're going to observe that this bound here is going to be here, and this is pretty much like our a minus x here, where f of x is actually equal to the cube root of x. So we can apply our identity directly to this integral, and rewrite this simply as the integral from 0 to 4 of just the cube root of x dx. So as we already know, the cube root of x is just the same thing as saying x to the 1/3 dx. And then we can use our fundamental theorem of calculus and find that this is just equal to 3 times the cube root of 4 to the 4th. All right, so let's do a more intricate example of where you may want to use this. So example 2. So let's find, I'm going to call this integral star. Let's do the double integral, say from 0 to infinity of 0 to x of sine of x minus y over x minus y dy dx. Alright, so let's focus on this interior integral first. Or you can focus on the exterior integral if you want to. So notice this is an integral with respect to y. So in terms of with respect to y, that means x is a constant as far as this interior integral here is concerned. So therefore, x is a constant here, x is a constant here. So this is pretty much like a f of a minus y here, because we have sine of, this is almost similar to like sine y over y if we use that integral shift identity, right? So that means, since x is a constant as far as this interior integral is concerned, that means our integral is precisely equal to the integral from 0 to infinity times, or composed with, the integral from 0 to x of sine of y over y dy dx. So as we may or may not already know, this function here does not have an elementary primitive. This is precisely equal to the sine integral of x. So therefore, this is equal to the integral from 0 to infinity of the sine integral of y evaluated from y goes to x and as y goes to 0 dx. So therefore, this is equal to the integral from 0 to infinity of the sine integral of x minus the sine integral of 0 dx. Now, what is the sine integral of 0 equal to? So the sine integral of 0, so remember the sine integral of x is the integral from 0 to x of sine of t over t dt. So if this is true, then this means the sine integral of 0 is equal to the integral from 0 to 0 of sine of t over t dt. And as we already know, if the upper and lower bounds are equal to one another, this integral is precisely equal to 0. So sine integral of 0 is equal to 0. So that means star is equal to the integral from 0 to infinity of the sine integral of x dx. So what do we know about sine integral of x? So one can find that the graph of sine x over x has this type of geometry where it has a limit of pi over 2 on the upper side and a limit of negative pi over 2 on the lower side. So that means since sine x is bounded above and is pretty much increasing on some interval, we can say that this integral is actually an infinite quantity. So that means this integral of interest actually diverges. Now, a couple of little side things that one may find interesting. So what if it's not direct, or can you get some other interesting properties about functions via this identity? Let's consider the integral from 0 to 4 of 1 over 7 minus x dx. So we know we can rewrite this integral in the form, the integral from 0 to 4 of 1 divided by 3 plus 4 minus x dx. So this is pretty much like our a minus x term here. So using our integral shift theorem identity, this is precisely equal to the integral from 0 to 4 of 1 over 3 plus x dx. So now we have two integrals here. We have this integral here and this integral here. So we have that the integral from 0 to 4 of 1 over 7 minus x is equal to the integral from 0 to 4 of 1 over 3 plus x. So do these functions here have any relationship to one another? Well, one can look at the graph of both of them. So the left one here, 7 minus x, that's 1, 2, 3, 4, 5, 6, 7. So that has a vertical asymptote here and is going to be located in its corresponding quadrants 2 and 4. And this function on the right-hand side, 1 over 3 plus x, is going to have a vertical asymptote at negative 3. And it's going to have a curvature in its quadrant 3 and the quadrant 1. So notice that these curves definitely do have some symmetry. And these points do cross at 2 comma, what would that be? 1 divided by 3 plus 2 is going to be 1/5. So these curves definitely do have some symmetry. And pretty much what we're looking at is the area, say from 0 to 4. So this area here and this area here truly are going to be equal to each other because these curves are symmetric about the line x is equal to 2. So that's, some interesting things that you can find. You can find other curves that have similar integrals, which is pretty much the idea behind transformations in general. So overall, this video is circled around the identity of the integral from 0 to a of f of a minus x dx is equal to the integral from 0 to a of f of x dx. So what if you don't have the integral from 0 to a? What if you have the integral from something else to a? So one can derive the following identity, which I'm not going to prove for you, but it's very easy to prove, and it is the following general result. That is the integral from a to b of f of a minus x times g of b minus x dx is actually equal to the integral from a to b of f of x minus b times g of x minus a dx. Now, this integral may look daunting, but is actually extremely useful in some cases, especially in terms of some beta function or gamma function identities later on down the road. So I hope you enjoyed this video to sort of give you an idea of some little shift tricks or substitution tricks that can be applied to more general functions in the form of integration.